I want to use. So if I don't know what to do, if your network is not good too, I don't know. Or the machine might go off anytime soon. We are talking about sound energy. We are saying that when we are talking about sound waves, when we are talking about the main waves, we said that we consider some two main parts of waves. We consider the longitudinal and we consider the what they call the transverse. You remember we spoke about that the other time.
Yes.
Yes. Okay, good. So we are saying that sound wave is a longitudinal disturbance. A sound wave is a longitudinal disturbance that consists of succession of compressions and refractions to which the ear is sensitive. So you realize that when we talk about sound waves, here we are talking about longitudinal wave. So the sound wave is a longitudinal disturbance. It's not a transverse. It's a longitudinal disturbance. And normally consists, if we are talking when we are talking about the transverse, anytime we talk about the transverse, we talk about how do you call it? The we talk about the crest and the troughs.
And pro.
Yes. Now, when we are talking about the longitudinal, we talk about compressions and rarefactions. And so here under sound wave, we are saying that sound wave is a longitudinal disturbance that consists of a succession of compressions and rarefactions to which the ear is sensitive. And so if you talk about sound, you're talking about the ear. Without the ear, we can't talk about sound. Likewise, when you're talking about light, we talk about the eye. Without the eye, we wouldn't be talking about light. You get it? And so if you're able to see, then we presume or we assume that you have light energy. You get it? Now, if you're able to hear, then we presume or we assume that there's sound. There's something called sound. As I'm talking to you, if you are not able to hear, you wouldn't be able talking about something called sound. And once you're able to hear, then you'll be talking about something called sound. So the sound is a longitudinal disturbance consisting of a succession of compressions and rarefactions to which the ear is sensitive. To which the ear is sensitive. Now, sound is a form of a wave motion, which is normally conveyed through an elastic medium from a vibrating body to the listener. So, sound is a form of wave motion, which is normally conveyed. It is conveyed through an elastic medium from a vibrating body to a listener. So you realize that I'm talking, so I'm vibrating. The sound is coming from a vibrating body. You get it? In my body, we have where the vocal cords and the rest, this thing is. So the sound is coming, so it is being conveyed from an elastic body, from a vibrating body to a listener. So you are the listener. So if you can't hear, you tell me, I say I can't hear. You get it? So it should be to the listener. And so it is conveyed from, if it was to be in this thing, we will say it is from a transmitter to a transceiver. And so you become the transceiver, I become the transmitter. So it is from an elastic vibrating body to a listener. That is it. Now, musical sounds are produced by various means. And so based on this phenomenon, we've been able to come up with various musical sounds or musical distance. And these musical sounds are normally produced from various means. From normal instruments you are talking about. We have the percussion instruments, we have the wind instruments, we have the stringed instruments. And so when we talk about the percussion instruments, we are talking about the drums, we are talking about the xylophone, we are talking about the africhua and the rest. When we talk about africhua, we have that those they've been using, the one they've been using for the jama, they'll put it on their hand and they'll be using it. Have you seen it? Sometimes it is mostly metallic. Uh, it is mostly metallic. Have you seen it, Robin? Robin, Robin. What is wrong?
I don't know. Suddenly it went no service.
Network. Network sometimes can be boring for her. So, as I was saying, sound is a form of wave motion which is normally conveyed through an elastic medium from a vibrating body to a listener. So it is normally conveyed through an elastic medium from a vibrating body to a listener. I hope I made myself clear. So sound is one example of what do you call it. Sound energy is one example of mechanical energy. It needs a medium to act, or it needs a medium for propagation. You got it. So sound energy needs a medium to propagate. So as I'm talking, I need a medium. Without the body and the vocal cord, you can't even hear me. You get it. So sound needs a medium. So sound is one example of uh, a mechanical wave. That is it. And we are saying that musical sounds are produced by various means. Now, we have three main means we are going to talk about. Basically, when we talk about music, we are talking about musical instruments. That is where we get a sound from. Now, the first the most powerful musical instrument is what do you call it? The voice. One of the most powerful musical instruments is the voice. So the voice is a musical instrument. Now let's come down to the man-made musical instruments. Now we have the percussion instruments. We have the percussion instruments. They include the drums, the dondos, and the rest. The xylophones, the frichua. I hope you've seen a xylophone before. Xylophone, sorry. I hope you've seen a xylophone before.
Yes, sir.
Good. They are example of
Yes, sir.
they are example of percussion instruments. Drums are example of percussion instruments. What do you call it? A frichua. Do you know a frichua?
Sir, please no.
You see, when they are doing the jama or when they are showing the jama, you see some guys they will be having something on their hand. They will be doing ka 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 like they are metallic sometimes. Ka ka ka. You see that instrument they've been using? The guys have been using. No, the jama people have been using ka ka. Nothing. We call it a feature. I call it. It's an example of a what do you call it? A percussion instrument. There's an example of a percussion instrument. And so that is it. Then we have the wind instruments. The wind instruments. They include the pipe organ, the atentebeng, the whistle. They are all examples of wind instruments. The pipe organ. I hope you've seen the pipe organ before. When you go to those old churches, like the Methodist churches, you see they have this
Yes, sir.
big organ here. So as an example of a wind instrument. And we
Sir,
have the,
I went to school.
you said, you went to a Methodist school.
Yes, sir.
Okay. Then maybe you might have.
But currently I'm in a
Okay. Even Catholic also, most of the Catholic schools or most of the Catholic churches also have those, what do you call it? Those instruments, the pipe organs and the rest. They normally have them, the church organs and the rest. So that is it. The atenteben, I don't know, it is normally wooden. They use wood to in molding it, the atenteben. Normally they've been playing it when somebody dies. They have some tune be like that. When you go to the JHS schools, they've been learning it. Atenteben is made up of wood. It sounds like a whistle. Mm. I don't know if you've seen that before, with some holes punched on it, around it. That is it. It's called atenteben. And we have the whistle. That one you already know. It's also an example of wind instrument. Whistle, an example of wind instrument. And we have the stringed instrument. The stringed instrument. The stringed instrument. The string instrument. A typical example is the guitar. Whether the bass or the lead guitar, they are all stringed instruments. And we have the violin. Violin is an example of string instrument. We have the violin. I hope you've seen the violin before. Do you play one?
Sir, please no.
You don't play any instrument.
Me, I want to learn how to play the drums.
Oh, okay.
I don't know.
Okay. So, example is the violin. We have the viola. We have the guitar and the rest. They are all stringed instruments. When we talk about the wind instrument, we have the clarinets, we have the trumpets. They are all wind instruments. Clarinet, trumpet, and the rest. Trombone, the tuba, and the rest. They are all uh, wind instruments. When it comes to the string instrument, we have the guitar, the bass guitar, the lead guitar, the acoustic. They are all guitars. They are all string instruments. The violin, the viola, and the rest. There are plenty. Normally, when you watch the orchestra perform, you see all kinds of instruments, and they all fall under one of these groups of this, the percussion, the wind instruments, and the string instruments. Now, it is interesting to note that even at the normal keyboard we've been using at church, that one we call it the synthesizer. It is called the synthesizer because it's just one instrument which has almost all the tones on it. When we say the tones, all the tones of the various instruments. So when you're using a synthesizer at school, or at home or at church, you realize that you have some parts, you have the drums tone recorded on it or synchronized on it. You can even get the xylophone beats or the tone synchronized on. You can get a pipe organ on it. You can get a church organ on it. You can get a whistle. Almost every instrument you have it on it. So when you with the synthesizer, you can use every you can use it to play every what do you call it, instrument. That is it. Now we call it synthesizer. That's what the boys have been calling keyboard, 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 keyboard. That is it. Then we have the piano. We have the piano. We have the church organ. We have the church organ or the pipe organ. That is it. That one normally they do it as part of the buildings because it is very huge. So it is stationed at one place. The pipe organ. So that is it. And the church organs too. The organs too. And we have different. We have the choir. They have the one with the steps, about 4 or 5 steps. They all have their names, the choir and the rest. That is it. The pedal and the rest. They are all instruments and they all produce sound. So that is it. Now all these instruments produce sound by causing an object to vibrate. So if you press the listen, the keyboard, when if you've opened the keyboard before or if you've seen the keyboard before, there's this pad on beneath each of the keys. So when you press it, that vibrates and it touches what we call the board itself, the sound board, and that gives the sound. And so whichever way, there should be vibration before there should be a sound, or before there will be a sound. When you when you strum the guitar, the strings vibrate. So that is when you blow the trumpet too. There's vibration that causes the sound. So that is it. So all these instruments produce sound by causing an object to vibrate. So an object must vibrate before there should be sound. When you play the drum, it vibrates. When you hit it, it vibrates, and the sound comes out. And normally the vibration is transmitted into the air as progressive longitudinal waves. And so it is transmitted into the air as progressive longitudinal waves. And when it happens, the particles of the air vibrate to and fro above the mean position, and the vibration being parallel to the direction of the transmission of the wave. That is basically everything I've said. And so that is it. And I told you that it's one form of mechanical wave because it needs a material medium for propagation, or it needs a material medium for their transmission. So that is basically it. Now let's talk about propagation of sound waves. Propagation of sound waves. Just as I said earlier, sound waves or sound needs a material medium for its transmission. And the medium can be gas, it can be liquid, it can be solids, it can be all other distance. So it can be gas, it can be transferred through gas, it can be transferred through liquids, it can be transferred through solids. They all transmit what do you call it? Sound waves, except vacuum. Except vacuum. Vacuum cannot. That is why it is impossible for spacemen to speak to each other when they are in space, because space there's no air, there's no solid, there's nothing. And so when they are there, there's nothing, there's no medium there, they can't speak to each other, because when they speak, each other can hear. And so when they are on the moonwalk, they can't speak unless by radio or any other things. So that is it. So sound passes through, can be transmitted through gases, can be transmitted through liquids, and can be transmitted through solids, except vacuum. So it needs, this means that it needs a material medium for its propagation. That is it. It needs a material medium for its propagation. That is it. Now, there is this experiment that normally they talk about to demonstrate that the necessity of air or other medium in the transmission of sound, the necessity of air or other material medium in the transmission of sound. And what they use is they use what we call the bell, the electric bell principle, where an electric bell is hung from a rubber band inside a bell jar. An electric bell is hung inside from a rubber band inside the bell jar, and it is normally connected to a battery and a switch. And so what they do is the bell jar is connected to vacuum pump. It's connected to vacuum pump. And when the key is closed, the bell is heard ringing. So when you close the key, you hear the bell ringing because the bell is an electric bell, so it is connected to battery. So immediately you close it, you hear the bell ringing. Now when the bell is ringing, air is gradually being removed from the jar, and so the bell is placed in a jar, and we assume that the jar there was air in it. Now the jar is closed and the bell is connected to the what do you call it, the battery. Now when it is connected, it will start ringing. Now as it rings, we assume that the air starts gradually starts what do you call it, the bell. As the bell is ringing, there's a gradual removal of the air from the jar. Now it gets to a certain point in time where the sound gradually dies, and when it dies, there's no what do you call it, no sound will be heard, and it simply just means that there's no medium for propagation of the sound, or there's no medium to transmit the sound. So as a result, the sound starts this thing. You can't hear the sound again. You get it? And it's just as a result of the air, all the air being removed as a result of the bell being ringing or something, or as a result of the vibration of the air in the jar. So that is it. So the sound from the electric bell gradually dies down as the air becomes less and less dense. No sound is heard when all the air in the jar is removed. And this shows that sound cannot be propagated in a vacuum. So it shows that sound cannot be propagated in a vacuum. Basically, that is it. That is it. So when you listen, when you take your test, you get a diagram of the distance, so you appreciate it better. That is it. You appreciate it better. That is it. Now, velocity of sound through solid, liquid, and gas. When we talk about velocity of sound, we are talking about the speed of sound. The speed of sound. And we are saying that sound travels about 15 times faster through iron, and iron is solid. So we are saying that solid sound travels about 15 times faster through iron than air, and in water about 17 times that in air. That's in air. So it means that the speed of sound depends on the medium through which it travels. So the velocity of sound in its medium increases with the order. And so solids, the velocity of sound is very fast, followed by liquid, followed by air. So it is only air which has we have the least, what do you call it, the speed, the least speed. And so we are saying that sound travels faster, about 15 times faster through iron than in air, and in water about 17 times than in air. And so basically that is it. So the order of increasing is something like this. Air, E stands for air. So air is less than liquid, which is also less than solid. It means that sound travels faster in solids than in liquid, and than in what do you call it, in air. And so sound travels faster in solid than in liquid, and it travels in liquid faster in liquid than in air. I hope I made myself clear. Hello.
Yes, sir.
Good. That is it. So light waves, on the other hand, and so but on the other hand, light waves on the other hand travel faster in air than is uh, travel faster in air than sound. You get it? Light, on the other hand, sound travels slower or relatively slower in air, but light travels faster in air than sound does. You get it? And so that is it. Light waves, on the other hand, travel faster in air than sound. And so, and that explains why an aeroplane is seen before the sound of the air is seen before the sound of the engine is heard. And also, he also explains why a gun is fired. When a gun is fired, a spark is seen before the report is heard. So that is it. So that is it. So when there's thunderstorm, you realize that lightning is seen before sound is heard, because sound light travels faster in air than sound. And so when you hear thunderstorm, you see the lightning first. You see the lightning first before the sound is heard. And that is it. and it's because as a result of light traveling faster in air than sound travels faster than sound travels in air. You get it? Exactly that. Now, factors which affect the velocity of sound in gas. The factors that affect the velocity of sound in gas.
Yes.
Good. Newtons show that the velocity of sound is proportional to Newtons. You know Newton, Isaac Newton's. He was one of the science, what do you call it, pioneers. Isaac Newton's show that the velocity of sound show that the velocity of sound is proportional
Yes.
to the root of pressure all over density. So the velocity of sound, according to Einstein, shows that it is proportional to the root of pressure. This is pressure all over density. It's proportional to, in accordance with the Boyle's law. And if the pressure of the fixed mass of air is doubled, the volume will be halved. This thing, when you do chemistry and the rest, you get it better. Hence, the density will be doubled. And so that this mathematics. So that's the ratio of pressure all over density will always remain constant. However, so he said that it's the velocity of sound depends on pressure and density. That is it. And so mathematically, when you have to look at this, V is equal to V is proportional to the ratio of pressure all over density. Pressure over density. You just bear with me that when the pressure increases, the volume, the velocity will also increase, and the density will decrease. Just looking at this mathematics, you get it. Just looking at this mathematics, you just understand this thing. You understand it. So the velocity of sound in gas is directly proportional to the square root of its absolute temperature. Now, that is according to Newton, and it's also in accordance to the Boyle's law. I don't know if you've done Boyle's law. Have you done Boyle's law? It's in chemistry or something. When you do kinetic movement of something. Forgotten the topic. You get to no.
Sir, you should not done it.
It's both in physics and in chemistry. So you get to the Boyle's law, the Charles law, and the rest. They are all there. They are all there. So that is it. It's dependent on pressure and distance. It's also proportional to temperature. So the velocity of this thing is also proportional to temperature. It's also proportional to the what do you call it? The square root of temperature. That means when temperature increases, the sound will also increase. So the velocity of sound increases with temperature, and so it is also proportional to temperature. And so the velocity, when you have two velocities, v1 all over v2, it is proportional to, or it is equal to uh, temperature 1 and all over temperature 2, all over temperature, all over temperature 2. So that is it. So when the temperature increases, the velocity also increases. So the velocity of gas, what the factors that affect velocity of gas is temperature affects velocity of gas, pressure, density. They all affect, or they all have a little effect on the velocity of sound in air. The velocity of sound in air. So that is it. Uh, that is it. That is it. Now, so sometimes giving this formula, they can give you work like calculate the velocity of sound in air at 0 degrees. If the velocity of sound in air at 16 degrees is 338 ms negative 1. And so this will be maybe the initial velocity, this can be the final velocity. This can also be the initial velocity, initial temperature, the final temperature. That is it. And it is gotten from V is equal to, this is V is proportional to T and this. And so the initial velocity is proportional to the initial temperature, while this is also proportional to the final temperature, something like that. And they can give you work on this. So you can be able to use this formulas to do it. Like they said, calculate the velocity of sound in air at 0 degrees Celsius. So the velocity of sound in air at 0 degrees Celsius. So we assume that T1 will be 0 degrees Celsius. T1 will be 0 degrees Celsius. Then we can, and if the velocity of sound in air at 16 degrees Celsius, so T2 was 16 degrees. So 16 degrees. At T2, the velocity V2 was what? 338 338 ms minus ms minus 338 ms minus. And they said calculate the velocity of sound in air. So that means they are calculating for the initial velocity. The first thing you are going to do is you are going to convert the Celsius to what do you call it? Kelvin. We can work it in Kelvin. You can also decide to work it in degrees Celsius. You still get the same answer. But when we are converting it to Kelvin, then that means Kelvin in Kelvin, this will be this plus 273. This will be 16 plus 273. That was what we are converting to Kelvin. And we can come and factor it into this equation and make V a subject. He said, I didn't hear you. Talk to me.
I said it's 289 degrees Kelvin.
So the 16, that's the 16 plus the 273. So next one will be,
Yes, sir.
so the T1 will be equal to, the T1 will be equal to 273. Because 0 plus 273 will be 273. Then the T2 will be, the T2 will be equal to 298, right? Or 289, sorry. 289. That'll be 289. That is it. So when we are done, then Kelvin, they are all in Kelvin. Then we are finding for the initial velocity. And so we can just do the arithmetic. So V1 will be equal to V1 will be equal to V2 V2 times root of the first one is root 273 all over 289 all over 289. What are you getting? V1 will be equal to V2 is 338.
320.
That will be 328.5. So 328.5
Yes, point.
ms minus 1. Ms minus 1. Have you seen it?
Yes, sir.
Good. There's some instance too, they can give you work. You realize I told you V can also be proportional to what do you call it? V can also be proportional to root of P, which is pressure, all over density, which is rho. You know, we write density like this. I also told you this one. I hope you remember. Uh,
Yes, sir.
Good. So in that case, can I erase it? You can, if you're done copying, let me know so that I erase it. Yeah.
So you can erase.
So we have this one. V was proportional to this, and when we have V1, V2, initial and final, we can have something like this. Now we are going to use the same principle. So when we have something like that, so that is it. The factors that affect this in pressure and density, we consider that one too. So we are saying that velocity is also proportional to the root of this all over this. So when we have final velocity and initial velocity, which is v1 and v2, we can have v1 all over v2. That will be equal to v1 will be equal to the root of this. So uh, you know, and variations when we are taking away this, we have to bring k to this. So that will be v is equal to that k is a constant. Have you done variations in commas?
So
Have you done?
hmm,
Oh, sorry.
it is physics, measurement.
Oh, okay, so proportion. So you bring k, you know that one. But here, because we'll be dividing, the k and the k will cancel. So I want to be any important to bring it. You get it? Have you seen it? So, uh, uh,
Yes.
so the density will be constant, but the what do you call it? The so v1 v1 will be proportional to p1 all over rho. Then v2 will be equal to. I want to take my time. V2 will be also proportional to or equal to k all over p2. That's pressure 2 all over the density. Yeah, the density will be constant. Yeah, the density will be constant. Because if you are using an instrument, then you are talking about the density of the instrument, which is constant for all of them. So whether V1 or V2, it will still it's still the same medium and the same density. You get what I'm trying to say? Eh?
So how did it become P1 all over P?
This is not P. This is rho density. I told you that V is proportional to this thing. V is proportional to pressure all over density, root of pressure all over density. Didn't I give you that one?
Yes, sir.
Yes. So with an initial velocity which is V1, and we are also considering the initial pressure, which is P1, but the density there is constant in this case. You get it? So when we are talking about the initial velocity, we can talk about it. When we are talking about the final velocity, we can talk about the final pressure all over the density rho.
But the rule is like P. Have you
How?
seen the one that you wrote at in front of the proportionality sign and thing?
Ah, okay. Uh, sorry. So you can just
This
write it.
one,
So you can
the
write it well.
V2 is
So you can write it well like this. You can write it like this. So when we are solving it, that will be like we have like this. So here will be P1, here will be P2. Have you seen it? Here will be P1, here will be P2. Here will be P1, here will be P2.
yes,
But
sir.
mathematically, it will become V1 all over V2. The P and the P will cancel. The row and the row will cancel because they are the same mathematically. Because they are all roots, you can open up. You can open up. We can do it in such a way that be you can open up and come and do it. P1 all over row divided by P2 all over row. And when we do the arithmetic, we are going to get root P1 all over P2. So realize that the first one we considered that we had the same expression in terms of temperature, and now we are getting it in terms of pressure. Are we getting it using the same this thing they gave us? The same thing they gave us. So when they ask a question like the same question I read it to you, when they like if they were to give you what it, in terms of pressure, this is the same formula I'm going to use. Hmm. Yeah, if you are given in terms of pressure, this is the same formula you're going to use. That is it.
So, sir, please, if they say find V1,
Yes.
what will be
And
the formula?
so find V1. Oh, this you just do change of subject. It is just change of subject. Or so V1 is equal to V2 times root P1 all over P2.
I get it, but
But what?
okay, it's okay.
How do you get it? If you don't get to tell me so that I know what to do.
So I now get it.
So let's do one. The velocity of a longitudinal wave. The velocity of a longitudinal wave. The velocity of longitudinal waves in a certain gas is 300 ms negative 1. It's 300 ms negative 1. The velocity of a longitudinal wave in a certain gas is 300 ms negative 1. It's 300 ms negative 1. When the pressure of the gas is 760 millimeter Hg, 750 mm Hg, 750 mm Hg. In other words, you can write 750 Pascal. When the pressure of the gas is 760, sorry, it's not 50, 60, 760 mm Hg or 760 Pascal. In short, you can use that one. If the pressure of the gas is doubled, calculate the velocity of the wave. If the pressure of the gas, is doubled, calculate the velocity of the wave. Assume the density of the gas remains constant. So they've already told you that we should assume that the density of the lesson remains constant. And when it remains constant, there's the same formula. There's a formula you're going to get. Did you get a question, please?
Yes, sir.
Good. I'm coming. So we are going to do it. So the first one, we are saying that the velocity of longitudinal wave in a certain gas is 300. So the first velocity here is 300. Ms negative 1. When the pressure is this thing, so when P1 is this thing, when P1 is 750, 760, 70 Pascal. Let me use this one. Now they are saying that if the pressure of the gas is doubled, so if pressure, so that means the last pressure, the final pressure, it will be equal to the double of this one. So if this pressure is doubled, calculate the velocity of the wave. So that means you calculate the final velocity or the last velocity. Do you get how I've done it? Do you get it? Do you get it?
So please, is it 424.?
3 ms negative
Yes,
1.
yes.
That's correct. That's correct. It's correct. It's correct. That's correct. That's correct. Can I clean it now?
Yes, sir. Magopa. Magopa. Magopa.
Now let's finish with the last topic so that. Now let's talk about notes and noise. Notes and noise. There's normally been getting it in interscience. They will say differentiate between a note and a noise. Hmm? Differentiate between a note and a noise. So we are going to talk about it. A note is a sound. A note is a sound produced from a vibration at one frequency. So a note is a sound produced from a vibration at one frequency. So do is a note. When I hit do is a note. Do is a note. So when you have a keyboard and you strike the first one, the sound that comes is a note. You are making a note. And so a note is a sound produced by a vibration at one frequency. So it's you strike it at a frequency. Now, a noise is normally produced by sources vibrating with no fixed frequency, and so by several sources producing an unpleasant mixture of sounds. And so when it becomes a noise, then that means it is number one, it is unpleasant to the ears. Uh, uh, it is from no fixed frequency. You get it? With the note is from one fixed frequency. So when I strike the note, when I hit one, you realize that the note sounds well in your ears. We call it a note. Now, it becomes a noise when it is from no fixed frequency and by several sources producing an unpleasant mixture of sounds. So you see, this is playing this, this is playing this, this is playing this, is playing this, and it's not making any sense. That becomes just an unpleasant to the ears. Then we call that one noise. So noise is from an unfixed, or it is from no fixed frequency, but a note is from a fixed, or it's from one frequency, or it's from a fixed frequency. That is the difference. One is from a fixed frequency, one is from an unfixed or no fixed frequency. Mm. Sources vibrating at no fixed frequency. The other one is from a source vibrating at just one frequency. Mm. So that's the difference between a note and a noise. Do you get it? That is how come one is unpleasant to the ears, one is pleasant to the ears. Mm. A note is pleasant to the ears,
Yes, sir.
a noise is unpleasant to the ears. So that is it. Now let's look out for some characteristics of sound waves. Let's look out for some characteristics of sound waves. Some characteristics of sound waves. A note is characterized by the following three sensations in the ear. So even with the note, it is characterized by the following three sensations in the ear. It is characterized by something called pitch. It is characterized by something called quality. It is characterized by something called loudness. So we are talking about three things. A note is characterized by the following three sensations in the ear. It is first characterized by a pitch. It is characterized by a quality. It is characterized by loudness. I'm going to explain these three things, then we are done for the day. We are done for the day. The next time we are going to talk about, we have some modes of vibration, stationary waves in sound, and the rest, Doppler effects, and maybe we'll finish. So it is characterized by pitch, loud. You can. We gotta check. Hold on, hold on. You come. You come. Yeah. Is it how much you go this thing? So I'll come. Ruben, so you go ready. I'll come. Ruben, Ruben, Ruben.
Yes, sir.
So that's
Yes,
it.
sir.
So the pitch. Let me just be quick. I have to talk to somebody outside waiting for me. So let me just be quick and listen. Oh, let's end here. Let's end here so that the next time we continue. Someone is coming to fix our light for us. So let me just go out and contact the person.
Sir,
So
please don't forget to upload the videos every day. I said in yesterday's video.
I will do it for you. I told you that yesterday the
See
phone
you.
went off, so I'll do it for you. Yeah.
So I think today it has come on, so do it for me.
So I'm going to. They are not coming to fix it. So after that, I'll do it for you. Don't worry.